Have you ever wondered why nature seems to prefer simplicity? Why does it seem to follow certain patterns and rules that make everything appear so harmonious? Why does a ball roll down a hill along the steepest path? What makes it choose that particular route over any other? Why does light choose the fastest route between 2 points? How does it know the quickest way to travel through different mediums? These questions have intrigued scientists and philosophers for centuries. They have pondered over the hidden mechanisms that drive these natural phenomena. There seems to be an underlying principle, a hidden code that governs the behavior of everything around us. This code is like a secret language of nature. This code whispers to the universe, guiding it along paths of elegance and efficiency. It is as if nature is always striving for perfection. Imagine the universe as a grand stage where countless events unfold every moment. Each event is a part of a larger, beautifully orchestrated performance. Each event, from the smallest atom to the largest galaxy, seems to follow a specific script. This script is precise and meticulously crafted. This script, it turns out, is written in the language of mathematics, and at its heart lies a principle of profound beauty and simplicity, the principle of least action. This principle, often abbreviated as PLA, asserts that nature is inherently economical. It always seeks the most efficient way to achieve its goals. It suggests that the universe, in its infinite wisdom, always chooses the path of least resistance, the path that minimizes something called action. This path is the most efficient and effective, but what exactly is action? And how does this principle govern the intricate dance of particles and forces that make up our reality? How does it influence the very fabric of our existence? Join me on this cosmic journey as we delve into the fascinating world of the principle of least action. Together, we will uncover the secrets of this fundamental principle. We will unravel its mysteries, explore its history, and witness its profound impact on our understanding of the universe. This journey promises to be enlightening and awe-inspiring. The principle of least action is not just an obscure mathematical concept. It is a profound idea that has shaped our understanding of the physical world. It is a fundamental principle that underpins much of modern physics, influencing theories and experiments alike. It provides a powerful framework for understanding why things move the way they do, from the trajectory of a baseball to the orbit of planets around a star. This principle helps us predict and explain the motion of objects in a way that is both elegant and precise. It is a principle that transcends the boundaries of specific physical laws, offering a unifying perspective on the workings of the universe. By applying the principle of least action, we can see the interconnectedness of various phenomena. Imagine a beam of light traveling from air into water. This simple scenario reveals the profound implications of the principle. We observe that the light bends as it crosses the boundary between the two media. This bending is not random but follows a specific rule. This phenomenon, known as refraction, can be elegantly explained by the principle of least action. The light takes the path that requires the least time, demonstrating the principle in action. Light, always in a hurry, chooses the path that minimizes its travel time. This choice is a direct consequence of the principle of least action. Since light travels slower in water than in air, it bends its path to spend less time in the denser medium, resulting in the observed refraction. This behavior is a testament to the principle's predictive power. This principle is not limited to the realm of light. It applies to a wide range of physical systems. Consider a ball rolling down a hill. The principle of least action is at play here as well. The ball could take an infinite number of paths to reach the bottom. However, it doesn't just choose any path. However, it invariably chooses the path of steepest descent, the path that minimizes its potential energy as it rolls down. This is another clear example of the principle of least action in action. This again is a manifestation of the principle of least action in action. The ball's path is determined by the same principle that governs the motion of light. The beauty of the principle of least action lies in its simplicity and universality. It is a principle that can be applied to a vast array of physical situations. It transcends the specific details of a physical system and provides a general principle governing its behavior. This universality is what makes it so powerful and elegant. It reveals a hidden elegance and efficiency in the workings of nature, suggesting that the universe is not a chaotic jumble of random events but rather a beautifully choreographed dance governed by elegant mathematical principles. This principle helps us see the order and beauty in the natural world. The story of the PLA begins in the 18th century with the French mathematician and philosopher Pierre-Louis Maupertuis. Intrigued by the elegance and efficiency he observed in nature, Maupertuis proposed a principle he called the principle of least action. He believed that nature, in its infinite wisdom, always acted in a way that minimized a certain quantity, which he called action. Maupertuis' ideas were initially met with skepticism and even ridicule from some of his contemporaries. His concept of action was not well defined, and his arguments lacked rigorous mathematical backing. However, Maupertuis' intuition was sound, and his work laid the foundation for one of the most profound principles in physics. Section 4. Euler and Lagrange, the architects of mathematical clarity. It was the Swiss mathematician Leonhard Euler who first provided a rigorous mathematical framework for Maupertuis' principle. Euler's contributions were not just limited to this. He was a prolific mathematician whose work spanned many areas, including graph theory and topology. Euler showed that in the case of a single particle moving under the influence of a force, the path that minimizes action is indeed the path that follows Newton's laws of motion. This was a significant step in linking the principle of least action with classical mechanics. Later, the Italian-French mathematician Joseph-Louis Lagrange generalized Euler's work to systems of multiple particles and developed a powerful mathematical tool called the Lagrangian. Lagrange's work extended the applicability of the principle of least action to more complex systems. The Lagrangian, denoted by the letter L, is a function that encapsulates the dynamics of a system. It serves as a cornerstone in the formulation of classical mechanics. It is defined as the difference between the kinetic energy, T, the energy of motion, and the potential energy, V, the energy of position, of the system L equals T minus V. This simple yet profound equation has far-reaching implications in physics. Lagrange showed that the path taken by a system of particles is the one that minimizes the integral of the Lagrangian over time, a quantity known as the action. This principle elegantly unifies various laws of motion. This result provided a powerful and elegant way to formulate the laws of mechanics and paved the way for further developments in physics. The work of Euler and Lagrange remains foundational in the study of classical mechanics and continues to influence modern physics. Section 5. Hamilton's Legacy, Bridging the Classical and the Quantum. The story of the PLA continues with the Irish mathematician William Rowan Hamilton. Hamilton took the work of Euler and Lagrange a step further, and developed a new formulation of mechanics known as Hamiltonian mechanics. Hamiltonian mechanics, instead of focusing on the Lagrangian and the principle of least action, focuses on a different but related quantity called the Hamiltonian, which represents the total energy of the system. Hamilton's work was crucial because it provided a bridge between classical mechanics and the burgeoning field of quantum mechanics. In quantum mechanics, the principle of least action takes on a slightly different form, but it remains a fundamental concept. Richard Feynman's path integral formulation of quantum mechanics, for instance, relies heavily on the concept of action.